Can you share my screen? I'm going to try to set it up in a way that I could project my phone to capture the screen. So,
Uh, okay, I'm going to download the your PPT now.
okay, switch this.
You are connected through phone, right?
Yes, sir.
Okay, right, cool. Great. I think the yeah, cool. Welcome, Ken. We will do the introduction in the meantime. Then I will download and then get the system ready. So
Okay.
let me walk through. Yeah, Deepa, please start the session. I will read the introduction to Ken.
Okay, 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 okay. Okay, fine. Good evening to all. And here we are with the next section. And today's special speaker is Ken, and we are having the topic on introduction to quantum machine learning. And here I invite KG to give a short intro to the section and welcome our speaker. Thank you.
Thanks, Deepa. Um, Ken or Kennel Surcoat is passionate about the quantum computing. He is a quantum computing enthusiast, researcher, experimentalist, and educator. He got his bachelor's engineering in communication engineering at Carleton University, Canada, where he got the fundamental element of quantum computing. At the time, that course was the first kind of first in the world, and he is also pursuing master science in electrical and computer engineering, including where he is studying quantum information at University Waterloo. The experience garnered from the industry and academy is incomparable for Ken. It has been for him, it is a bridge between the industry and then theory and practice, providing a holistic view of quantum computing ecosystem. Additionally, the opportunity to collaborate with the industry leaders and researchers, gaining insights into real world quantum applications and their transformative potential, nothing short invaluable for Ken. That he will come to know when Ken is delivering the speech. Ken has around 5 years experience. He's working for radio spectrum sensing quantum heterodyne. It has application fields such as quantum communication cryptography, where the manipulation of measurement of quantum states are fundamental to the operation. He was a student of quantum computing India 2 years ago, where Pradeep, Ken, and me were all interacted. We really, during the meeting, during the facilitation, Ken found very interesting people. Some of them migrated to Canada for their further study. Also, Ken planned to do while continuing his current work and maintain the momentum in the quantum learning and then building the solutions. He wants to remain at the forefront of the field of quantum computing, committed to advancing the field and then fostering a collaborative spirit and efforts. Please note that fostering collaborative spirit and efforts, which means Ken is ready to help and mentor whoever interested in the subject. The profound insights gained from industry, coupled with his Ken passion for education research, drives him to push boundaries of what is achievable in quantum computing landscape. With this introduction, I would like to invite Ken and as Kennel Surcoat, also known as Ken, to present this quantum machine learning session. Over to you, Ken.
All right. Thank you, KG.
Thank
Fantastic
you.
intro. Thank you very much.
Thank you.
As KG said, I met him 2 years ago when I became a student too of the courses, just like you guys here. And one of the key aspects of IQC, quantum compute in India, was the fact that it brought people together. And some of these people who I met, as KG mentioned, were so interested in quantum computing that they actually immigrated here and are looking to pursue quantum computing studies as well. So thank you for that, and thumbs up to the school too, KG. Okay, so let's begin. And I'm sorry about all the delays. Microsoft Teams, compatibility issues, whatever. But we made it, and we're able to improvise now. I hope everyone has the Jupyter notebook and it's ready to go. And you guys could hopefully follow from my screen here. And I'll try my best to keep things in focus here and make it as easy to follow as possible. Okay, so what is quantum machine learning for one? And how then would we see any benefits, or better yet, what can machine learning do for quantum computing, and what can quantum computing do for machine learning? So we know what machine learning is, and we know somewhat what quantum computing does, but do we know when these two things come together, what they are? And what it is an intersection of these two fields, and each one will present its own advantages to that field and assist it in some way. So, for example, or more like for definition's sake, quantum machine learning is an interdisciplinary field. It intersects quantum computing and machine learning. And what we hope to do is to harness the unique properties of quantum mechanics and enhance the capabilities of machine learning as well. But this isn't just one way. We have to examine it the other way as well. Well, how then does machine learning aid in quantum computing? And we have this definition here of what is quantum machine learning. And let's see now, what can machine learning do for quantum computing? So one thing, or a few things I'm mentioned here, is first, enhancing quantum algorithms. So machine learning can assist quantum computing by identifying and somehow mitigating noise or errors that might be present on the quantum computers. Issues of optimization, which we'll see later with the variational quantum algorithms, and in tuning these processes as well as that algorithm shows us. Another assistance machine learning could provide is in hybrid algorithms, where we're not just working with a quantum algorithm or a machine algorithm, but rather we're working with both of these together. And there are quite a few of these algorithms in process, the VQC, the QAOA, and a few more are coming in as well. Machine learning can also provide quantum computing assistance in error correction. So machine learning algorithms can be employed to develop error correction codes and strategies that help mitigate the noises that are present in the system. Quantum data analysis. Machine learning can be used to extract meaningful insights from this data as well. So one way machine learning does this is through the simulation and the feedback process, where we have quantum data and now we need to offset it through an optimization routine to attempt to extract some meaning out of it. Another example is with the optimization problem. Machine learning optimization techniques such as reinforced learning and evolutionary algorithms can all be used to assist quantum computing. And probably one of the more important aspects for the near term quantum computing is with quantum hardware calibration. If you guys don't know, there's a lot that goes into just calibrating your quantum hardware, in particular supercooled processors. It's susceptible to noise, decoherence, all sorts of issues pertaining to these. And if a machine algorithm can be set up to basically automate that process of optimization and calibration, well, that would be fantastic. So these are ways these two things can help each other. Now, let's look at it the other way now. What can quantum computing do for machine learning? And one aspect is the speed, okay? Quantum computing has the ability to provide exponential speed ups. One issue that machine learning, or actually just AI in general, will run into is as we increase the number of parameters that are available to be computed, well, that's going to take, in terms of time, it's going to take a while just to execute these growing parameters. So as these parameters increase, as we add more and more features, the behavior there becomes exponential in time. And eventually this will basically put or limit how many variables a machine learning algorithm can provide us in some time period. The next is the quantum feature space. So we work with the Hilbert space in the quantum computing, and our qubit is represented in that Hilbert space. When it comes to feature maps and increase in dimensions, the Hilbert space is the perfect. And yes,
my system is ready. I downloaded and then opened your worksheet. Sorry, your file. Can I open the IPyMB in my system? Share my screen.
Oh, actually, yes, please. I thought we were, but were you seeing my screen or?
Yeah,
are you
I'm
able
seeing
to
your
share my
screen.
phone screen? Okay.
No.
Yes, then go ahead. Go ahead,
Yeah,
and
yeah.
you could be the navigator. Go ahead. Sorry.
Yeah, you tell me, I will navigate. Okay.
Yeah. Okay.
Yeah, sure. Yeah, do you see my screen now?
Yes, I do. Perfect. Okay.
Yeah. This
So,
is more clear. Yeah. Let me go
okay.
back to the. No, I'm in this cell. Let me scroll to what quantum computer can do. Yeah, speed. You are here.
Yes. Perfect. So the feature map, quantum feature maps. So because we exist already, the qubit exists in that Hilbert space where we could work with infinite dimensions, and that infinite dimensional space is equipped with the inner product. This is the perfect space for working with increasing our dimensions. So for example, if we need to create a better linear separation classifier, well then increasing the dimensions is the way to do it, and quantum is equipped with that already. Another advantage or assistance that quantum can provide is with solving complex optimization problems. And quantum computers are basically designed, like not designed, but they excel in these optimization problems. The annealing process of D-Wave's hardware, it's perfect for these types of optimization. And with our gate-based systems coming in with IBM, these are going to be perfect systems as well for that. Quantum simulations. So quantum computers can simulate quantum systems accurately. So when we're ready to simulate, like say, weather patterns or climate models that has become the thing now, these are all natural processes. Even the behavior of molecules, these are all natural processes. And because of this, a classical computer would be limited in what it could provide in terms of simulation. So when we need to model a natural process, we need to be able to model that on a natural computer. And what is a natural computer? Well, a natural computer in that sense is a quantum computer, okay? Because it's able to mimic and simulate nature correctly because it is built off of the fundamental rules of nature. Another example is enhancing classical algorithms. So quantum computing and quantum mechanics are designed with matrix functions in mind. In fact, they are built off of matrix. And the mathematics that govern quantum mechanics, in its name, it is called matrix mechanics. So these processes just go perfect together, and the exponential speedups are available in these systems already. It's like they're inherited within the system. And so when it comes to solving huge matrices, million by a million, it's like a quantum computer could do these things extremely easy because of parallelism, entanglement, interference, and all the other features that come with quantum mechanics. Exploring new algorithms, new machine learning algorithms designed to leverage quantum properties such as superposition and entanglement. So we'll see now that as we move into the quantum, I guess, into quantum development, we'll begin to see new algorithms that implement all of these properties. One example is Grover's algorithm that implements the interference property very nicely, where we could have negative probabilities to identify or move through an unsorted list entirely. You know, there's no reason now to sort them or attempt to sort them. It's just keep them as they are, and Grover's algorithm can sort through it very easily. And handling big data. So quantum computers can handle these big data sets very easily because big data sets can be imagined as giant matrices with vectors moving through them. And this is just a natural property of quantum mechanics. And it would just happen that it would provide exponential speedups. Okay, and there are 4 approaches to quantum machine learning in general. These 4 approaches are where we have classical data and quantum data. Oh, sorry, classical data on classical hardware. So that's the CC, classical data, classical hardware. This is basically the definition now of machine learning in the classical sense, where we have the classical data being processed on classical hardware. Next, we have classical classical data on quantum hardware. And this is where the cusp of our machine learning, quantum machine learning, will exist, where we attempt to use this classical data, process it on quantum hardware, and attempt to extract meaningful information from it with all of the benefits of quantum, with the speedups and the entanglement process to identify data that's correlated in entanglement form, but that can't be represented classically because there is no entanglement representation classically. The next we have is quantum data and classical hardware. And we've seen now that we've answered this where classical computers can assist quantum data or quantum computing in that sense. And finally, we have QQ, where we have quantum data being processed on quantum hardware. And this is the future right here. Now, right now, we're probably in the first generation of quantum computers, and we won't see this quantum data on quantum hardware probably in the next, second or third generation, where we have now the ability to simulate quantum processes or natural processes, for example, molecular simulations, all quantum, on quantum hardware. And so this is where in the second or third generation design of quantum hardware, we'll begin to see this QQ. One of the reasons why it's not available now is because we don't have what is called QRAM, the ability of the quantum system to store its own superposition. You know, long before measurements, even before measurements, there has to be a way where a quantum system itself can store a superposition state without the wave collapse that would take effect if we have measurement, if we took a measurement. So we'll see that in the future. Okay. Next topic is quantum supervised classification. So this is where now we get into the design of quantum computing algorithms, more specifically, quantum machine learning algorithms. And the design that you see here in this image is basically of a variational form, where we have some classical data. In this case, this is just the NIST handwritten number data sample. And this data sample is encoded into a quantum system. And this encoding aspect of it is extremely important. It's not a trivial matter. It's extremely important how we encode classical data into a quantum state. And this image here is just showing the steps where we have some classical data being encoded into the yellow part into quantum data. And the blue part represents the parameterization of our circuit. This is where our training would take place. Why? Because this is where the parameters are in general, and this is where we would vary our parameters from a classical system. So we would offload the cost into a classical optimizer, and by tuning these parameters, we're able to then update this this blue section, and this blue section here has the name of an NZAT, and an NZAT is basically our optimization parameterized circuit where we do our training. And the green part here is our measurement, but we'll get into the different sections as we progress. Okay, so quantum machine learning involves several approaches for utilizing quantum computing in machine learning tasks. There are a few approaches, but we'll focus on these ones specifically because these are the ones that we could implement right now, and these are the ones that I have a few examples of. So the variational quantum algorithm is what is in this image right here. And so we have a yellow part, and we have a blue part, and we have a green part. And together, these form a variational quantum classifier. Quantum neural networks is similar to the variational algorithm in that instead of having a single yellow part, a single blue part, we have them alternating, where it would form a quantum neural network. So you'd have the yellow, the blue, followed by the yellow, the blue, and repeated, so on and so on. This is the structure of the neural network. The support vector machine in its construction is just the yellow part. So it's the yellow part followed by the yellow part followed by the yellow part from that diagram. And we'll see that some more as we progress. Okay, so one of the important aspects of quantum machine learning in near term is the ability to have parameters within our circuit and be able to change these parameters, tune them to say. And parameterized circuits are circuits with parameters within the gate structure itself. So from the diagram here, we see that we have a gate RY, and the parameter here is just the star, which again is a trivial matter, just it's a placeholder, okay? Then for the X, it's a square, another parameter, and for the Z, it's a circle, again, just other parameters. And parameterized circuits are also called parameterized trial states, variational forms, or NZATs, and offer a way to implement algorithms on near-term computers. You know, and why do we need these? Because our qubits are extremely noisy at this moment, you know, and we have a limited number of them. So what could we do with what we have? Well, what we could do is we could offload some of that cost, some of the cost function associated with our quantum algorithm, and offload it onto a classical optimizer where we can implement some gradient method to identify where we can minimize these costs. And parameterized quantum circuits, if you could scroll down to expressibility and show the diagram, and yeah, perfect, yeah. So one parameter for ensuring that we have a good parameterized circuit is whether or not we're able to use the Hilbert space efficiently. And if we look at the diagram on the left or the right diagram, we have an idle circuit where we have this blank block sphere. And on the single qubit, we just have an identity gate. The identity gate doesn't do anything. And so 0 in means 0 out. So there's not much in terms of utilizing the Hilbert space there. When we go to circuit A and we implement a Hadamard gate, well, then we get onto the equator of our block sphere. And now if we implement Z rotation, then we have access to that entire equator. But that's just a very small subset of utilizing the Hilbert space. And so circuit B shows us now an even richer utilization of that Hilbert space where we have the H gate, the RZ gate, and the RX gate. And it's not a full, proper, efficient utilization because we have these two dark spots that are appearing, and they appear on the ket plus and the ket minus orientation of that Bloch sphere. So that concentration means that we haven't fully homogenized our space in there. And so as we move over to the arbitrary unitary gate, and you could think of the arbitrary unitary gate as the U3 gate, where the U3 gate now is the general form of all qubit gates. And with the unitary gate, we could access and utilize the Bloch sphere and the Hilbert space specifically in an efficient manner. And this is what it means to have the expressibility here, is like how expressive is our circuit and whether or not we're using that space efficiently. Okay, if you could scroll down, KG, to the next. Yes, entanglement capabilities. Perfect. So the entanglement capabilities here is extremely important in our parameterized quantum circuits. If you look at circuit A is just made up of single qubit gates, and these single qubit gates can be easily simulated classically in the general sense. Why? Because there's no entanglement within those circuit A. And so because of this, that means that we're going to miss out on the richness and identifying correlated data structure, or any structure within our data that we're trying to analyze. Whereas if we look at circuit B is like circuit A, but now it has entanglement. And this entanglement is extremely beneficial in the sense that you could think of it as this analogy. In circuit A, you think of it as being in the classical sense. And in the classical sense, you're trying to mix oil and water. And in the classical sense, these things wouldn't really mix together. In fact, you can't really mix them together. But with entanglement, okay, in the quantum space, well then, yes, you can actually mix oil and water, and you could do it very well with entanglement. Okay, so this is just an analogy to highlight these two differences. And this entanglement measure, or entanglement capability, has its own measurement. So we have the Meyer-Wallach measure, where you have no entanglement, so that means your circuit has 0 entanglement capabilities, versus you have entanglement and your circuit has at least a 1 in terms of that measurement. And entanglement is extremely important in the sense that it gives you access to, correlated information within the system. And we'll see how entanglement plays its role as we proceed. Oh, actually, perfect. So below this, I have a snippet of code. Yeah, sorry. Sorry, KG, go back to entanglement capabilities. Yeah, okay. So below that image right there, the yellow part, this is just a snippet of code that shows that why entanglement is crucial, and we have it within that code, and we define it as linear entanglement. So again, we'll see this play in as we proceed. But now constructing a parameterized circuit. So parameterized quantum circuits tend to be used for, I guess, 2 things. Encoding data and creating quantum models for optimization. And in that sense, it's really easy for us to create parameterized quantum circuits. And this is done through our import statement, where we would import parameter, say if we want to specify just one parameter. Oh, could you scroll down a little, KG? Yeah, a little more. Oh, too far. Yeah, right in here in the code here. Okay. So we could see now that we could import our parameter, and we could import the parameter vector. So the parameter is where we specify just one, and you could see this in the code, versus the parameter vector where we specify a list. And if you could scroll down a little there, KG. Yeah, so keep scrolling down. So yeah, right there. So in the first diagram, we could see that we're just parameterizing single qubit gates, but this is just the manual way of doing it. If you want to parameterize one gate versus if you need to parameterize an entire list of the circuits, then we would implement the parameter vector in that sense. Okay, and it's pretty straightforward. The Python code is pretty straightforward and explanatory, and it's there if anyone needs to play around with it. Yes, so let's move on to the next topic, quantum information encoding. So this is one extremely important aspect of machine learning is the encoding aspect of it, where we take the classical data and we turn it into quantum data. Now, we've been doing this for a while now in the sense that you take classical data and transform it to quantum data. Well, what you've been doing inadvertently is machine learning, okay, believe it or not, where we take some quantum data or classical data and we encode it into our quantum system. This encoding aspect also comes by many names. One name is a feature map or feature mapping, okay? And this is done automatically. Most people don't even pay too much attention to it, but this is done in that sense where we don't even think we're doing machine learning, but in actuality, we are doing machine learning. So mapping our classical data into quantum data is not a trivial task as it is in a classical system. So if we look at the diagram that here is in the classical sense, we have some data and we feed that data directly into the machine learning algorithm. And in the end, we get some predicted information, okay? In the quantum sense, we take the classical data, we need to encode it, then we run our quantum machine learning algorithm, then we take a measurement, and then we make some prediction based on that. And looking at what's in there in these white blocks, we see for our quantum system, it's the state preparation, a unitary evolution, and a measurement. And so it's not a trivial task as it is in machine learning where we just have the data and we input it. In the classical sense, in the quantum sense, we need to encode that information, okay? And another reason why this is important is if we look to the right of that image, this here is the qubit map of our 16 qubit system, our 16 qubit processor. One thing to notice is qubit 0, qubit 6, qubit 15, and qubit 9. These are the ones that are on the outside. Well, these aren't connected directly. So that means if we have to entangle those things, those two qubits together, well, that would be an issue because those two qubits are not connected in any way, shape, or form. Okay? So this is where we have to not only encode our data in the sense that we have to prepare it for the quantum state, but we also have to be aware of the quantum processor's configuration as well. So when we add entanglement, we're not adding entanglement on two qubits that are nowhere near each other in that sense. Okay, so moving on. Yes, so let me see. Okay. So in order to solve supervised machine learning tasks based on classical data sets, the quantum algorithm requires an information encoding and readout steps that are in general a non-trivial procedure. And it's very important to consider them during runtime. The strategy of how to represent the information as a quantum state provides the context of how the design of our quantum algorithms are going to be, what speedups we're going to get out of it, or how the data itself is going to be classified. And these arguments call for a thorough discussion on data encoding and the approaches and routines of how we would implement them. Information can be encoded in many ways for a quantum system, but we will only focus on a few of them. We'll focus on basis encoding, amplitude encoding, and angle encoding. Now, each one of these encoding schemes has its own advantages and disadvantages, but one of them will stand out more than the other, and that's the entanglement, or angle encoding. Angle encoding could be considered as a higher encoding scheme. Okay, so let's look at basis encoding. So basis encoding is primarily used when we have real numbers in our data. And real numbers meaning that they're all integers and they're not floats, okay? And in the image we have there, we could see that in the input side, the orange, we have input samples, feature x1, feature x2, represented by 5, 6, and 4, 1. And so what we'd do is we'd represent these numbers as their binary equivalent and now use that as our encoding scheme. And I've provided a bit of literature here explaining the hows, but overall, it's basically taking out a number that represent our feature and turning that into a binary digit and using now that binary digit to encode our data. And if we scroll down a little, KG, there's a sample of code. Yeah, there we go. So this sample of code here basically just lets you define that basis encoding. And again, you could play around with it. If I had decomposed this a little more, I'd decompose this circuit. So instead of having these blocks, I decompose them into their what's inside them, then we would be able to see that. But I left it up here for anyone interested. You can add your decompositions to it in the code there, as you could see. Okay, next, amplitude encoding. Amplitude encoding, this technique uses amplitudes as coefficients on our quantum state. So for example, we have input classical data. We have x1, x2, x3 as 6, negative 12.5, 11.15, and 7. And as you can see, it's not just int, but rather it's floats as well. And what we do then is we normalize, and then we use that normalization equivalent of x1 as a coefficient on our quantum state. And so we could write out the amplitude encoded form as the lighter blue part here at the bottom. So angle encoding, very straightforward. And again, if we scroll down a little, scroll down to the code sample, we could see how now we translate that amplitude encoding into code here. Now, most of this is done, I wrote this up to do it manually, just to show you guys that this could be done in the manual sense. But there are automatic functions that will do this for us that we'll see later. But for the sake of understanding, this is how it's done. So, and let's move on to angle encoding. So angle encoding is a higher order type of encoding. And this one here is one of the ones that's used primarily. Why? Because it's a higher order encoding where if our feature doesn't have a linear separable class definition, then we could add dimensions to it where we could go from 2D to 3D, so to add like a linear plane in between our data where we can have that now to separate the classification. So angle encoding allows us to do that very easily. And angle encoding in itself is known better by its Qiskit name, which is ZZ feature map. Okay, and so we could see how the angle encoding is done. We have our features, our x1, x2, x3, x4, and we'll use that now to encode it within the general definition of our qubit state. KG, if you could scroll up just a little about the photo, there's a formula I just want to break down Yeah, there it is, right there. Okay, so this equation here is the general form of our quantum state. And some of you should be, actually all of you should be familiar with it, in that this general form has a cos and a sine coefficients on our ket 0 and our ket 1. And so the angle encoding would basically put in our x features directly into the cosine and the sine. And there's another flavor of angle encoding that we'll see later, but this is how angle encoding is done in that sense. And as we do each state then is Kronecker product or tensor product with every other state till we have this giant state of our quantum data, our quantum encoding. Okay, and so now let's look at the code just at the bottom of the image here. And we have an example here where we encode the data points 3, negative, 6.2, 5.55, and 3.5. And it's a very trivial matter where this is basically angle encoding at its simplest form. Okay, yes. So arbitrary encoding. So arbitrary encoding, it just means we're gonna arbitrarily or just generally just attempt some encoding function. And we're not bounded by any particular rules as long as we're able to encode our features correctly, where we're able to provide proper classification of our data. Dense angle coding is a slight generalization of angle encoding that encodes 2 features per qubit. So whereas angle encoding encoded 1 feature per qubit, dense angle encoding encodes 2 features per qubit. And how we do this is we use the phase, again, so going back to our equation here, where we have the general form of our qubit state. And we notice that the relative phase is still on there. We would have a global phase on the end of the cos or at the beginning of the cos. But as we know, when we take measurements, that general or that global phase disappears. So the relative phase does stay in place. And so that relative phase, because it has a parameter of theta, we can encode a new or a different feature in that as well. And so we're able to encode 2 features per qubit within our general form of our state vector. And as we move down, we'll see like this is an example of one of our automatic encoders. So efficient SU2, where this circuit encodes 12 features. So we're not just bounded by arbitrary encoding where we can do 2, but there are other designs as well where we can encode many, many more features efficiently. So for example, the efficient SU2 encodes 12 features with only 3 qubits. And again, this is automatic. So we could see when we define X, we have our list here of features. And from that list, we could feed it directly into our encoded circuit. That takes in circuit and it binds the parameters of X with our theta value that we would have defined in the efficient SU parameters. And this is what we would get out of the encoding of the features of the efficient SU. So actually scroll down a little here, KG. Oh, sorry, we've gone too far down. Could you scroll up a little? Yes, there, perfect. So these 2 images represent the same thing. Most times we won't see what's inside the block, and we'll just call that block a unitary. Okay, it's just a block. Okay, but what's inside it is this this feature map that we could see. And so there are different ways that we could see this. We could either see it as it is with all of the features encoded, or we could see it as a block, and that block would just be called a unitary matrix. And we'll see these come into play as we proceed. Okay, so scroll down a little and let's talk about the data encoding circuits. which is just below these images right here. Oh, where is it? Data encoding circuits. Scroll down. Oh, is it on the summary? Let me see. Oh, okay. Sorry. It's above. Okay, scroll up. Right below arbitrary encoding, below that diagram, we have a little subsection there called data encoding. And this is where we have, yes, so keep scrolling down a little. Yeah, keep going down. Okay, data encoding circuits. Okay, so these data encoding circuits are what are built into Qiskit. And again, they're not bounded by being called data encoding circuits. We could also call them feature maps, feature mapping. Data encoding and feature mapping are the same thing, just different words for the same thing. And so Qiskit has these built in. So for example, we have the poly feature map, the Z feature map, the ZZ feature map, and the state preparation. And I left a bit of code right below that, already predefined, and you guys could play around with the code just below that. So I've commented some of it out, but if you remove the comments, we could see how each one, the Z feature map, each one maps to itself, or not maps, but how each one, the mapping of how each one takes place. Okay, so summary, down to the summary. So if you could scroll down some more, KG. Oh, yeah, above summary. Perfect. So summary of our encoding. All we've done here in our variational quantum circuit is the yellow part. Okay, this is what we've done here. We've taken our classical data and we've encoded that data, and that is just the yellow part of that image. Okay, and next we're going to look at the blue part. Okay, the blue part here is what where our training would take place, where we would vary our parameters, and this is probably one of the more important aspects as well. Not that any of them are less important, they're all equally important. Okay, so the variational quantum algorithm. Scroll down a little, KG, next topic. Yeah, perfect. Okay, so as the name implies, the variational quantum algorithm basically requires us varying a parameter in that circuit. And we could look from left and moving right. We have the variational quantum circuit, we have a measurement, and we have a classical optimizer. And how this works is like this. We have the variational quantum circuit that we've defined with our parameters. We're going to take a measurement, and our measurements come from our Hamiltonian. And that Hamiltonian gives rise to some cost function that we need to minimize. So if when we take a measurement, we get a 1, right? And we're trying to minimize the cost function. Well, we know that 1 isn't good enough. We want at least -1, okay, if we want to minimize our cost function. And so what we'd do then is we would offload that onto a classical optimizer using some gradient-based optimization to update the parameters to tell us, okay, we need to go a step left or a step right or a step somewhere because the first parameter we got isn't the ideal parameter and we need to do an update again. And so the classical optimizer would do that, optimize that new parameter, feed it back into our variational quantum circuit, and we would repeat that process again. And this is the loop that we see here, okay, where we have the variational quantum circuit, we take a measurement, we offload that measurement to the classical optimizer, that optimizer updates our parameters, and we circle back and forth until we get that minimum that we're looking for. Okay, variational quantum circuits. In the most general sense, a variational quantum circuit is a circuit that depends on a set of parameters, as we've said before. Okay, and typically a variational quantum algorithm queries the quantum computer, does some output of the parameterized circuit, and again, this circuit is called an NZAT. Okay, and then we update. Then we get some cost function, then we update, and that is just like a loop that we repeat. Measurement. So measurement is by far the trickiest thing here. And I hope you guys understand measurement in its general sense. Okay, when we take a quantum measurement, what we're doing is we're saying we have some wave, and now we need that wave that's in this superposition to collapse into a classical representation of information. So when that wave collapses, it's either going to give us yes or no, or +1 or -1, okay? Despite everything. So one way to think about this is a single qubit could represent all of the information in the universe, and then some more. Like you name it, it could represent all of the information in the universe. But once you measure that, what you get is yes or a no, which is meaningless in the general sense, where you could say, okay, well, you could represent all of this information, but then I take a measurement and you give me a yes or a no. It's like, what is the meaning of life, existence, and everything? And the computer gives you back an answer of yes. It's like, well, yes, no, no, yes. Like, what does that mean? So measurement in that sense is what we're doing from a quantum computer. It can't provide you with anything more than just this bit of classical information, a yes or a zero. Okay, and so a variational method is a technique to approximate phi of psi. Okay, and phi of psi is some energy value. So when we take the energy value of psi, sorry, just my phone just fell over here. Okay, so when we take the energy value of psi, we do it with the Hamiltonian, sandwiched in between the bra and the ket. Yeah, and this gives us our our expectation value of our system. And when we repeat that many times, then we get an averaging out of that expectation value. And one way to define this is to say, since the ground state of the energy system is the lowest energy eigenstate, by definition, it holds that. We have psi, well, we have the bracketed psi star, Hamiltonian, psi star has to be less than or equal to some new value that we're going to take again. So if we've taken a measurement and our expectation value and it comes back as 0.5, well, then we expect that it's not going to be 0.6 if we're trying to measure on our next measurement value. And so this is why it has to be less than or equal to a new update. So if we get a 0.5 and we take an update and we get a 0.4, then everything is good. Everything is working perfect. If we get above a 0.5 to say a 0.6, then we know, well, we may have already reached the minimum and there's no sense going any further. Okay, so this is what E naught means in that sense. And by minimizing the expectation value of our trial state, phi of 0, finding parameters theta for which the expectation value is defined, it becomes as small as possible. So if we run through that loop, it becomes smaller and smaller and smaller. And this is where we're able to obtain that cost function that we're able to feed into the classical optimizer. Okay, so the classical optimizer is then used to update the circuit parameters in order to maximize or minimize, most cases minimize, at a -1, we minimize the objective function / the cost function. And these steps are repeated in that quantum classical hybrid loop until we get that value that we're satisfied with, that minimum value. And this is basically the definition now of that variational quantum classifier. Okay, so going down to our variational quantum classifier, we have done the yellow part and we've done the blue part. And we've explained the measurement, right? Okay, so now let's take a look at the VQC process. So the VQC process is defined within these 4 steps. Okay, we have the embedding feature map, loading the data into the quantum system, classical data into the quantum system. We have the NZAD variational circuit, our quantum classification circuit where our training takes place. Measurement and assignment labels. So from our measurements, we could have like our assignment loop, so we could get zeros or a string of zeros to tell us how we're doing, or we could get some other value. But these are like where our costs are identified. And finally, the classical optimization loop, where we implement some gradient based optimization where we could find that minimum. So explaining embedded feature maps, we have a few options. We have basis embedding, we have amplitude embedding, and we have angle embedding. Angle embedding is that higher order where we're easily able to add dimensions onto our system if we're having difficulty classifying in a linear format. These embedding processes, I guess we could call them, correspond to feature maps. And so we have the Z feature map, we have the ZZ feature map, and we have the poly feature map, okay, that do these embedding for us automatically, okay? Instead of having to do it manually, assigning each variable. So now we could have these do it automatically for us. And these are all built into the Qiskit SKD. Okay, next we examine the NZAD variational circuit. And the NZAD variational circuit have a few options in themselves. But again, when we're defining an NZAD variational circuit, we need to verify that there's expressibility and entanglement, because these things give us access to, you know, non-correlate data in the classical sense versus quantum, where we could see whether or not our data is correlated in a higher dimension or other forms, or by like what structures there are within our data that can't be identified in a classical sense. So this is all done through our variational circuit, ensuring that we have proper expressibility and entanglement. And Qiskit offers us a few of them, N-local, 2N-local, poly-2 design, real amplitudes, the efficient SU2 that we saw earlier, excitation, preserving, and QAOA NZAD. And all of these give us some variational circuit that we could properly train and do classification with. Now, they're not just bounded to classification. We could do, what is it? We could do, well, okay, in chemistry, where we need to say identify the lowest state of a molecule, let's say, right? And we want to simulate that molecule. Well, there's special NZAD circuits that will allow us to do that, including their algorithms. So the QAOA NZAD is one of those that is optimized for chemistry, where we need to identify the lowest energy state of a molecule or attempt to simulate. So some of them are designed, well, not so much designed. Some of them are better suited for certain tasks versus others are suited for other tasks, okay? And examining measurements and assigning labels. The final step in the measurement step, which estimates the probability of belonging to a class by performing certain measurements, it's equivalent to sampling multiple times from the distribution of possible computational basis states. Now, these computational basis states is just one form of the measurement where we're looking for a string to define our classification. But what if we don't want a string? Then we could obtain other expectation values to say, okay, well, if we're getting a 1 and we want to minimize to a -1, well, then we know what we have to do then, okay? And finally, let's examine the classical optimization loop. And the classical optimization loop, as well, I guess if you're familiar with machine learning, 1 second there. Okay, there we go. Yeah, and so if you're familiar with machine learning in the classical sense, well, then you're pretty familiar with the optimization methods that are available for the Adam, the Kobola, the SPSA, and the sequential least square programming. So these are just optimization routines that are available to us in our classical loop. Now, some of them might perform better than others for a specific task we're doing, for the classification task that we're doing. And so at times we'll need to switch between different optimization routines to attempt to find a better minimization value, a better cost function. And so we could do that very easily. We could actually design it so that we could run through all of these optimization routines and then compare them to see which one performed better. Okay. Okay. So now let's get into the Qiskit machine learning API. And we'll start from the bottom and work our way up. So this is the Qiskit machine learning module, and there is an initial set of functions here that will be built over time. And actually, some of these I've seen that are already becoming deprecated. So, but for now, it's a good reference for us to see like what functions and how it's structured for the machine learning APIs. Okay, so let's begin from the bottom. In Qiskit, we have the circuits, we have operators, we have the gradient framework. So our optimizations, we have vanilla, we have natural, we have stochastic. They're all in there for us. And other optimizers as well. Next, we have the upflow QNN. And what this does, it allows us to operate on our circuit. So as the definition implies here, allows users to mix quantum circuits and quantum mechanical observables. So if we want to connect two circuits together, that type of thing, then we would call on these functions to do it for us. The two-layer, same thing. It's a special case of the upflow, which takes in a feature map and loads our data into it and allows us to train our NZAT. The circuit QNN doesn't have a measurement operator, but it measures the circuit directly and translates that into an output circuit of probabilities. We'll see that we won't see that one much, but definitely the quantum kernels we'll see, and quantum kernels come from kernels in the classical sense. So we'll see how these behave naturally. And finally, above kernels, we have the QSVR and QSVC. So we have the regressors and we have the classifiers, but for the sake of simplicity, we'll just focus on classifiers. And finally, we have our VQR, again, regressor, and our VQC. And this function basically allows us to do that entire variational circuit that we saw with just that particular function, okay? It has simplified that entire process for us. We just feed in its parameters and it provides us with our feature. And finally, we have the PyTorch Connect, which allows us to wrap our neural networks with quantum networks in that hybrid fashion. So instead of using classical optimizer of unknown names, we could use the PyTorch connectors or scikit-learn or any of these. We're not bounded to any particular forms. We're very flexible. Okay, so scroll down, KG, to chapter 8, train and parameterize quantum circuits. Keep going down. Yeah, there we go, perfect. So try to center these two diagrams for me on the screen as best as you can. Okay, so train-in parameterized quantum circuits. The first image, we saw how this was done with the variational form, and we explained it thoroughly. When we examine the VQE and we look below that, the green and the yellow are the definitions of that VQE. And we see that we have our unitary blocks of each one, and the green arrows pointing to, if we decompose them, what's in those blocks, what's in the green block and what's in the yellow block, okay? Now, above that, the green feature map and the yellow variational circuit, we have this, this tiny function written here. What this tells us is we could express our state as a combination of those two blocks, where we take in an x parameter and we take in a theta parameter, and basically that defines our state as we move through that block, okay? And below that, we have our label data. So we see our classical label data, how that is encoded into a feature map. And from there, next to the feature map, we have our variational circuit, our NZAT, as we've seen, that's dependent on that theta variable. And then we could take parity measurements from that circuit to provide us with some cost function, or some cost function that we could use then to optimize. And this provides us with our labels. And this is basically the variational circuit right there. It's like simplified. It's like we have input labels, classical data encoded into a feature map. We have our variational circuit, we have parity measurements, and we have some label on the outside. Okay, now let's go down to the code and try it out. So scroll down to the code. Yeah, let's try it out. Okay, perfect. Now, this is just a extremely simple, we don't want to complicate things here with training that may take a while or be complicated in any sense. So we input, or we import all of our functions, our packages, and now we'll use some ad hoc data set for training and testing data. So this is what we have here. We define our dimensions, our feature dim 2, training size 20, test size 10. Very simple, keeping things very simple. So this is basically just classical optimization. We're just cleaning up our data and preparing it to be used. In the next block, we have our feature map. So this is where we define our feature map. And the feature map, you know, is part of the encoding scheme. So our feature map is equal to our ZZ feature map. And we pass in the ZZ feature map feature dimensions, which is 2 up there. And how many times do we want this repeated? And you could decompose the code to see, like, actually, we've done it, but we have 2 displays. We have the unitary block of that feature map, and we have the display of what's inside it, okay? And this is all we've done here. We've just encoded our data into our feature map. And the feature map we're using is the ZZ feature map. And the ZZ feature map has linear or entanglement. And this here, we specify linear entanglement, but we could also specify circular entanglement, okay? Because entanglement is extremely important to us. Why? Because it cannot be simulated easily in a classical sense. It's like, well, if it can be simulated classically, what's the point? You know, just run it on my computer and end the story. We don't want that. We want higher order entanglement, where we're able to see or identify any structures in the data, any correlations between features, like all of these things that might be hidden from the classical world. Okay. And if we scroll down to the next block of code, we define here our NZAT, okay, our variational form. And in this case here, we're going to use the 2local. Okay, so we're using the 2local to create our NZAT. And with the 2local, we specify the feature, well, the number of qubits. And here, with the 2local, we're able to do something quite differently. Here, we're able to specify what rotations we want to employ. Okay, we could specify that as well. You know, we're not bounded by any specific rotations. We could specify our own rotations, or we could design our own rotations from the U3 general block to specify some rotation. Okay, and this is what we see here. So again, we've created our NZAT. It can be represented as a unitary, or we could see what's inside it, and this is all the red stuff that we see there. Next, we put these two circuits together. So if you could go to the next block of code. One sec. Okay. So our next block of code, we combine our two circuits that we've created. We combine our ZZ feature map and we combine our NZAT. Okay. We combine our encoding aspect and we combine the NZAT. And this is what we have here. Now, again, we could add the decomposition to this circuit.draw to see what's inside of this. But I think you guys get the picture of what's in here. Okay. And if we could scroll down to the next block, KG. Yep, right here. And now we're going to feed that basically into our variational quantum circuit function. And you can see that the variational quantum circuit function takes our feature map, and it takes our NZAT, and it takes our classical optimizer. So voila, we've just completed all the blocks automatically of our system. We have our encoding scheme, we have our NZAT, and we have our optimizer. So we have our class, we have our encoding, we have the variational form, and we have our classical optimizer all rolled up into one. And very few lines of code, we could begin our training and our classification. And this is what we've done here. With this, just these two lines for something that appears so complex, we could simplify it with just these two forms. And from our data, we're just testing our ad hoc data set, but again, there wasn't anything specific about it. We're just checking how well our implemented VQE was at classifying our data. And it says our testing accuracy is 100%. Okay, so now what I ask you guys to do, if you want, is to play around with that code and try it out. It's very simple, but that should be enough to get the ball rolling for you guys into quantum machine learning with the VQE. And let's move on to our next section. If you could scroll down to the next section, KG, there we go. So there's no free lunch in the sense that we could just keep adding qubits and adding our circuit repetitions, add in depth to a circuit in an unlimited fashion. If you could scroll down some more, KG, keep that barren plateau, just to pull up the block of image right there. So what ends up happening as we increase the number of qubits and we increase the depth of our circuit, like by repeating, say, our NZAT many times, what ends up happening is our gradient begins to, well, not our gradient, our surface begins to disappear, okay? And this is from the fact that we are increasing the number of qubits and increasing the depth of our circuit. And if our gradients begin to disappear, then they become useless at attempting to find any global minimas. Okay, and this is a problem in that sense. It's like, then if the surface is completely flat, how would we find our global minima? Now, some roughness is good, but too much smoothness is a terrible idea. If we smooth out our surface and remove all the local minimas, well, then that's a great thing, because then we just have a global maxima that we need to find. Okay, so it's an extremely tightrope walk onto how deep we can make a circuit and how many qubits we can implement in our attempt at our classification. Because if it's too many, then the surface becomes too smooth and we would need a high precision to attempt to find it. which wouldn't be a problem for future quantum computers, the second and third generations, because they'll have so many qubits that will have that type of precision. But for near term, it is an issue for us. So barren plateau is caused by a large and deep expressive parameterized quantum circuit. Barren plateau landscape correspond to gradients that vanish exponentially with the number of qubits as well. Therefore, an exponentially large precision is needed to navigate through that landscape. Again, in the future, when we get awesome quantum computers, there won't be any minima or global minima that can't be found. Okay, but for now, with the NISQ and noisy qubits, that is an issue for us. Okay, so cost of the barren plateau. So from those two images, we could see how as we increase the repetitions in our circuit, well, our minima, our global minima begins to turn into like well, what is that? Is that a dip? It's certainly not a global minima in that sense, where it's like it's a deep valley, right? Now, in a true surface, on a flat surface, that tiny dip would still be a global minima, okay? But for the sake of the qubits and the noisiness that's associated with them, well, maybe the noise could create its own global and local minimas as well, taking us away from the actual global minima. So that is an issue with this. And this is how and why it happens right here in that image. Okay, and let's scroll down to strategies to avoid and mitigate in global minimas. Okay, and yeah, let's pull up that image. So a possible idea is to initialize and train parameters in batches in a procedure known as layer-wise training. Okay, so layer-wise training has been the most effective at reducing and avoiding barren plateaus. So if we look at the layer-wise training here in the diagram, we could see as we iterate, we lock in our values. So for example, iteration 1, what we do then is we lock in our value. So we train that layer, and then we lock in those values. So we train it, we accept some cost function that's associated with it. Okay, that's good. Now let's iterate again. And so in iteration 2, you could see that we've already optimized the first layer, we've locked in that value, and so now we will train the second layer. And same thing with iteration 3. So now we've locked in 2 layers, and now we're training the third. And so that way, this reduces the depth that the circuit sees, or the depth that our quantum computer sees when it needs to process this data, to just individual layers, and we lock in those values so that way we avoid that. And as we could see with the local versus the global cost, this basically tells us that as we increase the number of qubits on the x-axis here, the horizontal axis, we could see how other circuits and circuit depth representations behave. But the one that behaves the best is the local cost and constant depth of the layer-wise training. And local cost means instead of having a measurement on every qubit, okay, instead of having to measure every qubit, we only measure a few qubits. And so that reduces the overall Hamiltonian of our Z functions, okay? And so this reduces the overall burden on the quantum processing system as it attempts to provide us with our data. And these are the ways to reduce the barren plateau. And this is something that we have to keep in mind when we're working with quantum machine learning algorithms, either in the variational form or other. Okay, and so we can move on now to our last topic, which is, if you could scroll down, KG, some more, which is the quantum support vector classifier. And we have two comparisons here in the image. If you could scroll down a little there, KG, to give us those images. Perfect. So the support vector classifier has this form where we only repeat the feature maps, okay? So if you look at the image next to it, the blue and what is that, the tan color there, the ANZAT, if we had to structure that as a support vector classifier, we'd only have the blue feature maps, okay? We would not have the ANZAT, okay? And this is what the image of the QSVM structure is saying, is that we only have feature maps and nothing else apart from a measurement when we're ready. Versus, say, the QNN, which would be feature map, ANZAT, feature map, ANZAT, feature map, ANZAT, alternating like that. That would be the quantum neural network. Whereas the VQC is feature map, ANZAT, 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 okay? And so this is one way to distinguish these three classifiers in that sense and their structures. So quantum classifiers, unlike classical methods, quantum classifiers requires pre-processing to encode classical data into quantum and then train the parameters in the quantum neural network. Using different encoding methods, we can benchmark the optimal classification performance that tests the data. Types of quantum classifiers, well, we have the variational quantum classifier, we have the quantum neural network classifier, and we have the quantum support vector classifier. Perfect. If you could scroll down a little there, KG, to quantum classifiers. Yep. And we're just seeing how these different classifiers work. So the red, blue is the neural network, quantum neural network. And the gray at the bottom is just the support vector classifier. Okay. And so now let's get into support vector classifiers and feature maps. If you could scroll down a little. So classical machine learning methods requires us wrangling their input data into different spaces to make it easier to work with, or because new spaces offer properties that are convenient and or related to the model analysis. Okay, and so SVMs classifying data using a linear hyperplane. A linear hyperplane works well when the data is already linearly separable in the original space. But that is unlikely in many data sets. And so the workaround is to add a new space or a new dimension that hopefully provides us with some linear separation of our data. And so quantum kernels and machine learning is one way to do this. And again, our encoding, as we've seen before, our quantum embedding, but it's the same thing, quantum encoding or feature mapping, all the same terms referring to the same thing where we take classical data and we transform it into quantum data. And this is a very important aspect of designing quantum algorithms because they directly impact the computational costs. And if you could scroll down, KG. Yeah, scroll down some more. Yeah, and just pull up this diagram right here. Perfect. So feature mapping and encoding functions. So in the diagram below, we have psi of 1 of x is equal to x1, psi of 2 of x is equal to x2. Okay, now let's say for whatever reason we don't have proper separation in those planes or classification. We need a nice linear model to provide us with a nice way to separate our classes. Well, then we could increase our dimensions, and we could increase our dimensions by saying, okay, well, this new dimension, I'll call it as psi 1 and 2 of x is equal to pi of feature x1 and feature x2. And this is what this diagram is showing us here, is that each one of these is a different way to represent that information in a higher dimensional form, okay? And so we're not just bounded to any particular form. We could specify our own, but each one has its own, and each one will play its own role in the classification we are trying to do. So for example, if we have the circle versus a moon versus an XOR versus some other form of our data that we're looking at the data. So sometimes our data is set up in a circular form. We have an outer ring and we have an inner ring, and we could say, well, that's circular. Okay, so this is what this is saying here in that sense. It's like we could specify these different additional dimensions to help us separate it based on whether or not it's circular or some other form. And the way this is done is with the kernels, a function of two data sets that measure the similarity between our features. A quantum feature map naturally gives rise to a kernel. So all of these feature maps and coding schemes, whatever names we want to call them, well, they have an associated kernel with them already, okay? And so this kernel gives us our measure of similarity, and this is all from the dot product. Where are we? Operators, perfect, yeah. And so the dot product is what we have here, where we have the bra and the ket squared, okay? So this is if we want to reduce our value to a singular form. Well, we could get that. Or what if we want to represent it as a matrix? Well, instead of bra and ket, why not have ket-ket? And ket-ket gives rise to our density operator, okay? So when we have bra-ket, that's reduced to a single answer, versus when we have ket-bra, sorry, not ket-ket, ket-bra, then we get a density operator, a density matrix. And so there are ways to represent that. We could represent it as a singular form, our kernel as that singular form, or as a density matrix, you know. And combining kernels may improve our classification accuracy as well. So we're not bounded to just one kernel, but rather we could combine different kernels, take properties of different kernels and combine them. So let's say this one is good, but it doesn't have this, and this one has this, but it doesn't have that. Well, then we could combine them, and now we could extract the properties, the constructive properties of each one, okay? And so this is what's being said here with the kernel, where we could add these different kernels together. And here is, okay, and if you could scroll down to hyperplane, we have an image block there. Okay, one sec. And we have the hyperplane. So if we look at the first block, we could see how our data is circular in form, right? That's the A right there, okay? Now, if we look at B, we see that our data is, it's not linearly separable, but rather it appears to be exponential in that sense, okay? So looking at our data just on the graph. And if we look at C, we could see that C is like these two moons combined together. They're not circular and they're not that exponential, but it's called moon, okay? And so different dimensions as we increase the dimension. So if we take moon and we add a dimension to it, well, how then would we implement a hyperplane between them? And this is where we showed earlier that we have these different combinations that we can add. And we have the XOR finally, which is D. It's like, okay, well, what do I have to do to X1 and X2 to create a hyperplane that's able to separate that XOR data on that map? And so this is where we'd have to play around with these different functions, see how they behave, see how the classification is. But again, this is things that we have to consider. And so for example, B, looking at example from A here, so A of A, right? That is the both circles there. And we go to B, image B. We'll see that that circle form, if we increase the dimension, then we could see that we have a nice separation in 3D with that new dimension where we can implement a hyperplane between them where we can separate our data very nicely, and we could have proper class identification. And C is, or C here is basically just showing that hyperplane in place. So looking at it in the 3D perspective and looking at it in the 2D top-down perspective, this is what we have here. Okay, and so if we could scroll down a little to QCV and QSVM. So these two are related. The variational quantum classifier are just linear methods in a quantum feature space. Using quantum kernels as a measure of similarity on that data basically is what connects these things together. And a quantum kernel can only be expected to do better than classical if it is hard to estimate classically, meaning that we need that entanglement in there. Because if we don't have that entanglement, then classical data could do it. But classical computing cannot truly represent how quantum states are entangled, and this is where that strength comes from. Okay, and we could scroll down to choosing quantum kernels in practice. So if you can, KG, yeah, that's perfect. Okay, so what this shows us here is ways to, how do we choose a proper kernel that's going to provide us with what we have? And this representation is with only a single qubit, okay? And so take a quantum kernel that is hard to estimate, parameterize it, then optimize it. Simple enough. Take a quantum kernel that is easy to estimate, add entanglement, parameterize it, then optimize it. This is the Gaussian kernel, okay? Now, we have an extremely important kernel here that's in the works, and it's called the D-log kernel. And this D-log kernel offers a super polynomial speed up, okay? This is the known case where we have a quantum advantage, and this is all done on 1 qubit. So if we look at the first image, we could see how it's easy to classify 2 classes +1 and -1 on a single qubit with a hyperplane attached to it. And in the second diagram, the middle, this shows how we could exploit the data that's hidden within we could exploit the structure of the data, okay, that's hidden from the classical perspective, okay? This is all that the middle image is saying. It's like, oh, okay, there is structure to this data. So if we look, we have this triangle here, but these triangles, the red one and the blue one, each of these points are their own data points. But we could exploit structure in the data to say, oh, all of this data is related by some means. And so we could say that, oh, this data is just the representation of the ket plus, and the blue data, despite its 3 points, all of it can be summed up and represented as the ket 0. And with that, we could implement a hyperplane between those 2 data points, within those data points, and classify them very easily. And the third image is just a basic represent. It's not anything in particular. It doesn't represent anything. But when we're doing this type of classification, this is the type of behavior you would expect to see. This is the type of information that would be drawn out as we attempt to classify and structure our data. And that's all it's showing right here. Okay. So the Qiskit feature map for support vector classifiers. Again, we've seen these before, where we have the Z feature map, we have the ZZ feature map, and we have the poly feature map. All of them could be used for support vector classifiers. The structure of the support vector classifier is the fact that it just repeats our feature map. Okay, it doesn't have an ansat that comes in. It just repeats our feature map. Okay, and this is what allows this type of classification, is that we can do our training, we can do our optimization directly from the Z feature map with our data. And this is what's being said here. Okay, and finally, let's try out some code, which is the section below. And again, we just have our data set. This data set is just an ad hoc. Okay, so we prepare our data set. And now, again, if we look at the second block, we have our mapping. So we're going to, again, implement our ZZ feature map that we already know of. Yeah, keep scrolling down, keep scrolling down. Yeah, keep scrolling down. Ah, there we go. Okay. And so we have here our ZZ map that we're going to define with our ZZ feature map. And we've seen this in play many times. And instead of the V variational quantum classifier, we're going to use our quantum kernel that's basically going to do everything for us. Okay, so again, it's just plug and play here, nothing special about it. Simple 2 lines of code. And the second block of code, we have our ZZ kernel construction, our ZZ kernel with our constructed circuit. We're going to specify our training samples or sample train. And the next block of code, we're just going to simulate this to provide us with our data. And again, we could calculate the transition amplitude, our measure of similarity. And if we scroll down to our matrix train. Oh, perfect, right there. Okay, so now we define our matrix train. And again, there's nothing special here. We don't even have to show our training kernel matrix and our tested kernel matrix. That's just added code. But sometimes we need to verify whether or not we're on the right path and everything is properly optimized. And one way to do this is to view the training kernel matrix. And this is the matrix that provides us with how our data is related to our data points. So how our data is related with our data. And the diagonal line tells us that when we take our data and compare it with our original data point, so one data point compared with our data point measure of similarity, well, we get this diagonal line here that basically tells us that everything is nicely correlated and properly optimized. And it's a square matrix, so again, add into it. The test kernel matrix here, well, it's a test kernel. It's not a square matrix. It's just a matrix to tell us, well, whether, actually, it doesn't tell us much in that sense, so we could just overlook it. But what's important is the train-in kernel matrix. Okay, and if we scroll down to support, quantum support vector classification, yeah, and we scroll down a little. So this basically just walks us through what we spoke about above. And now that we have our pre-computed kernel classification score, we could take that and compare it to classical kernels and see how they behave. And this is what the 2 blocks here do, is that we take what we had originally, the pre-computed kernel classification test score, and we compare it against the classical kernels, and we could see how well it did with that. Okay, and so again, there's links in here, feature maps and data sets where you could go and play around with and see how these things behave, but pretty straightforward. And we conclude here. So quantum machine learning represents a breakthrough fusion in 2 cutting-edge fields, quantum computing and machine learning. This emerging field holds immense promise and potential, but again, it's still in its early stages. There are many advantages that quantum computing provides to machine learning, and when we combine these 2 things, we see that we have this dynamic force where we could reinforce both of these together. There are several challenges and complexities, quantum algorithms that need to be developed. Some we've seen in their early stages, the VQE and or the VQC and support vector machine, the quantum variation. Quantum hardware, there are some limitations as to how far we could go with this because of the limited number of qubits and how noisy they are. Okay, so quantum machine learning heavily depends on the development of that quantum hardware. And again, it's it's advancing. Okay, just last year we were at 128 qubits. This year we had 400 qubits. So there are updates being done. And right now it might seem like a trivial matter to say, oh, well, classical computers can outperform quantum computers. Yes, they could do it because, well, we only have a few qubits right now. Okay, that's like saying some analog computer could compete against a digital computer with just a few bits. Okay, but here we are now, several years later, several decades later, with thousands, or not even thousands, trillions of bits, you know, and we can't make that argument anymore where we could say, oh, an analog computer can blah, 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 blah. Like, oh, well, why bother? We'll just take the analog signal, translate it to a digital, and do our digital processing there. Well, this is the same thing that's going to happen with classical, is that we're going to take our classical data, translate it to quantum, and voila, okay? So let's not be nearsighted in our views to say that that there are limitations and nothing will materialize out of it. No, there are limitations, but every day there's some new breakthrough, there's some new technology that's happening. And so it's best to attempt to remain or to see what's going to happen in the future and best prepare for it right now. And right now, one way to do this is by learning the applications of quantum computing, in particular machine learning and machine learning algorithms. Okay, and that is all. I hope we were able to do it in time. And I guess if anyone has any questions, or sorry that I may have bored you guys.
No problem. Again, it is very, very useful. There are few questions. One is, I will come from the first one. There is a question why we have back-to-back decompose. Remember we have recursive decompose, 3 decomposes the long.
Right. Yeah. Okay. Sure. So the decompositions, in fact, I would recommend that you try it out, like remove some of the decompositions and see what you get. So you would probably get like a unit vector, right? But when we look inside the unit vector, there might be other unit vectors as, sorry, not unit vectors. There might be other unitary matrices. That's what I should say. There might be other unitary matrices within that unitary matrix. So we need to apply another level of decomposition to get just the gates, to see the gates within it. So this is why I have, you might see like a chain of decompositions, because unitary matrices within unitary matrices within unitary matrices up until we get to just the gates themselves.
Yeah, thanks, Ken. There is another question from Dr. Nalini. Usually we will take data the 80-20 or 70-30 for training and testing, but here we are taking 20:30. Is that any specific reason for that one?
No. Because we're live and we're running this live, I don't want to take any more than what the system may provide me in a few seconds. You know, I don't want to have to train a huge data set like while we're live on air, because, you know, well,
okay.
Yeah.
So yeah. It is for live session, it was reduced to Nalini. Then
Exactly.
There is one more question from how to add layers in QNN as like classical YAML.
Oh, okay. So adding layers are quite easy. So let me see if you could go back to one of the code samples. Just okay. Let me see there. So scroll down to, yeah, keep scrolling down. Actually go up. Where are we? Okay, keep scrolling down. Let me see. Not in the encoding. somewhere in where we could see a ZZ feature. Oh, actually here. Okay, slow down. Okay, so somewhere in here. Okay, so if we look at the ZZ feature map, right? The code here, circuit is equal. Okay, we have 3 qubits. Now we have repetitions, right? Is equal to 1. Well, this is how we add the layers. So we could specify how many repetitions we want. Do we want it repeated twice, 3 times, 4 times? And so this is how we would add those different layers.
Okay, good. Then final question is, how can we find patterns from diagram C if data is in the circular fashion? I think it is about the kernel, the hyperplane.
Yes. So if we could go back to that section with the image. Right, it's under choosing quantum kernels in practice.
Yeah.
So keep scrolling down.
Yeah.
Oh, maybe we've gone too far. No, it's close to.
Yeah.
Oh yeah, perfect. Okay, so I left out a lot of the detail here as to how we would extract structural data here, but I did leave the blue highlighted area here. So this paper here by Jennifer Glick basically walks you through it nicely and explains how exactly.
Great.
Yeah. So I would recommend just browsing through that paper to get a general idea of how, but I left that explanation out because it's a bit more involved.
Great. Yeah, team, we will share that notebook file, Jupyter notebook file in the Google Drive. Remember OneDrive, MyQT OneDrive, where we are sharing all recording and then resource files. There you can access this notebook and then read through. There is a wealth of information composed by Ken. Now I think we are end of the session. Deepa, can you?
Yes, KG. Before that, shall we ask the participants to put on their video for a screenshot?
Just one few seconds.
Just a few seconds, fast.
Yeah, quick. Please keep video on. Smile. You are under camera. Great. Yeah, please quick. We can move on to the, because it is a yeah, quick. Thanks, RB. Bijit, thank you. Yeah, Deepa, I think we can take.
Okay.
Yeah. Great.
Okay, thank you. And now
We can take one more copy. One more.
Okay.
Just now RB come into focus. Cool.
Done.
Yeah.
Thank you.
Thanks, Deepa.
And now I call upon KG to deliver the vote of thanks.
Thanks, Deepa. Uh, it is a great session, Ken. Thanks for your sharing your insight knowledge onto the quantum machine learning. Based on our interaction, I know that you are one of the right person to share knowledge on quantum machine learning to the right thing, and then the way how you handle the questions. All those things will give you a feel that if there is something help is needed, there is a person who can be contacted. Please support our community with your knowledge, wealth of knowledge. Thanks a lot. You are doing already a lot of things for the community. I know. In the interest of how to say those things, I'm not sharing all those things. But community team members, please believe that Ken is sharing a lot of knowledge and then serving our community with multitudes of activities. Thanks, Ken. Thanks for your support.
Hey, and thank you for
Continue
having
doing
me.
this.
I hope I didn't bore anyone or get anyone confused.
No. It was an amazing session. It was those
Yeah, and
people.
I want to. I apologize for the technical difficulties we're having. I still don't know what the issue is, but hopefully we'll have it solved.
But those changes worth for attending this session.
Okay, excellent.
Then I thanks all the team members who are all joined, and yeah, Nalini. Yes, madam. Hello, Dr. Nalini.
There's a question in the chat window, KG.
Okay. Okay, Nalini, I will connect you with Ken. Later, you can talk it. Yeah, talk with Ken. Okay. Yeah, that will be taken separately, one-on-one, offline. I will do that one. Then thanks for all the team members who are attending. Yeah, yes, Abhijit, the whole notebook file, Jupyter notebook file will be uploaded into OneDrive. We can download there. It is a 14 MB file, so it won't be shared in WhatsApp, but it will be uploaded into OneDrive from where you can download. Yeah, yes, that is true. And it is very, very true. Thank you. Thanks for all the attendees and then the organizers of this event, Deepan, Pradeep, Gomati. Thanks all. Thank you. Have a great weekend. Enjoy. Bye bye.
All right. Cheers.
Thanks, Ken.
Cheers.